So good morning, everyone. It's a pleasure to be here. And I've titled my talk today, Genetic Algorithms, a Practical Technique for Optimization. So today I will cover an introduction to optimization, to explain what optimization is about. I'll explain how genetic algorithms work, GAs for short, and I will introduce several applications. So to put this into context, as Professor Lee said in his introduction, my area of expertise is artificial intelligence. And genetic algorithms are part of a broad toolbox of artificial intelligence techniques. Broadly speaking, artificial intelligence can be broken down into two parts: knowledge-based intelligence and computational intelligence, or data-based intelligence. There's a lot of focus at the moment in neural networks and deep learning, which is essentially just very large neural networks, which deliver machine learning. But that's just part of artificial intelligence. There is a long tradition in other aspects, particularly the knowledge-based intelligence aspects evolved, well, really from the very start in the 1950s and certainly through the 1970s and 80s. And but today I want to talk specifically about genetic algorithms. So they're part of the computational intelligence side of artificial intelligence. And for me, when you're building an AI system, you really want all these different tools working together, because every tool can do a specific task, and a powerful AI system will use multiple techniques together. And I may come back to that point towards the end, but for the bulk of this talk, I'm going to focus on genetic algorithms. And genetic algorithms are for optimization. So to understand what optimization is, effectively, it's finding the best value or combination of values. And by best, I mean the one that has the highest fitness. So if you imagine the simplest possible example, where there's just one variable x, and you're trying to find the best value of x, you're looking for the value of x which has the highest fitness. So a one-dimensional example might be x could be age, and the fitness could literally be, in the human context, your fitness. But anyway, you're trying to find the value of x with the highest fitness. And you'll notice in this example here that there's the highest value here. This is the so-called global optimum, but there are also some local optima here and here. And in identifying this as the global optimum, we are assuming that the function is bounded, i.e. that there's nothing beyond to the left or the right that's higher. So we're assuming it's a bounded function, and this is the global optimum. And what you're usually trying to do with optimization algorithms is find that global optimum and try to avoid being fooled by these local optima. So one dimension is very simple. 2 dimensions is a little bit more complicated, where here we're trying to find the optimum combination of x and y. Again, we've got local optima and a global optimum that we're trying to find. But in practical problems, there may be very many dimensions. It's hard to represent it on a slide, but there may be very, very many dimensions. So it becomes quite complicated. And the main point about optimization algorithms is that you're trying to find that global optimum without having to test every single possible combination of variables, because that would be computationally explosive. It could take thousands of years if you're sampling every possible combination of your variables. So the whole point about optimization algorithms is that you get to your optimum without having to test all the possibilities. You have to test some possibilities, but not all of them. So looking at this example here, I now want to move on to just to set the scene, a little example of finding the optimum in just this scenario. What I'm going to do is run a little video of software finding this global optimum, but I've made the highest peak quite narrow, so it's hard for the algorithm to find. Before we get on to that, just a few points of principle of genetic algorithms. They are population-based form of optimization. That is to say, you maintain a population of candidate solutions, and the algorithm works on the principle of survival of the fittest. So Darwin's principles, that the best solutions survive. And each individual candidate solution is a point in the search space, and its chance of reproducing depends on its fitness. So the fittest solutions reproduce and generates a new generation which shares many characteristics with the parent generation, but is different. And because only the best parents are selected to reproduce, the population evolves in the same way as biological evolution. What you try to do when you design these algorithms is to first of all explore and then exploit. And that means you start by trying to explore the whole landscape to make sure you found the global optimum. And then exploit means that once you've found the area of the global optimum, you want to get right to its peak to get to the absolute specific optimum rather than just near it. So those are the principles. There are other approaches to optimization, but what makes genetic algorithms distinct from all these ones that are listed here is that all these just have a single candidate solution and they try to improve it. But with that sort of approach, there's always a risk of being trapped in the local optimum. Genetic algorithms are distinct in having a population of candidate solutions that evolve. So coming back to this graph, I said I was going to show you a demonstration of it, and to make it a little more challenging for the genetic algorithm, I've made the global optimum quite narrow. So this is my software, and to the left of the screen, you'll see a representation of those three peaks again. And the tallest one is this one I'm pointing at here. I've set a few parameters here and I've just set it going. So it's just started now, the genetic algorithm. And what you should see in the left-hand picture are lots of red dots moving around. Every time they move, every red dot is a candidate solution. And every time they move, that's a new generation. And to start off with, the dots are mostly focused over here on this local optimum. But you do see red dots appearing elsewhere as it's exploring the search space. And right now you suddenly see a jump in the fitness because it's started to find this global optimum. See, the fitness is now going up and the population has shifted. The population is now shifted to be predominantly around this global optimum. So it was initially drawn, the population was initially drawn to a local optimum, but because it was exploring, it was generating candidate solutions outside of that local optimum. It found the global optimum, and then that became the focus of the evolution. Just want to show you another example now, a bit more sort of practical. That was very sort of conceptual. Now, practical example. Tuning the parameters of a model helicopter like this one. Now this helicopter is controlled by a so-called PID controller. That's proportional integral derivative control. And that has a number of parameters to adjust. And it's effectively a tuning problem to adjust those parameters. This is what the helicopter looks like when it's flying. And you'll see it's moving up and down a bit, but it's pointing forwards in quite a stable way. And what we wanted to do was make sure that the helicopter was able to maintain that forward pointing position by adjusting its PID parameters. And we did it by tethering the helicopter, tying it down so it could only move left and right, and adjusting its parameters so it was able to maintain a forward position. So here you are at the start, and it just swings to the right. It's just not, it's hopeless. It's not, and then swing back to the left and then swings to the right. So it's not pointing forward at all in any kind of stable way. After 5 generations of genetic algorithm to adjust its parameters, it's a little bit better, but it's still pointing to the right. After 14 generations, we switch it on now, and very rapidly, it moves to pointing forwards. It's now much more stable. As soon as you switched it on, it started pointing forwards. And after 27 generations, it goes straight to pointing forwards, very stable. It's had its parameters adjusted by the genetic algorithm. And if we look at this graph of performance, we can see that the genetic algorithm tuner worked better than the version tuned by the engineers. It had a lower error. And what you've got here with these two sets of the graph, it starts off being pointing up to the right, and then we reset it and it started off pointing to the left. But each time the genetic algorithm adjusted its parameters very effectively. So with that context and brief description of how they work, I now want to go into a little bit more detail of the of how genetic algorithms work, a bit more of the detail of them. So each candidate solution is a point in the search space represented by a chromosome. So in our two-dimensional landscape, our XY parameters, just imagine a point where X is 2 and Y is 6. That could be represented by this chromosome 2, 6. But genetic algorithms are always binary. So using binary numbers, you would represent it as shown here. So an 8-bit binary chromosome. In fact, in genetic algorithms, we don't normally use conventional binary coding. Tend to use coding called gray code. It's very similar. You represent your numbers by zeros and ones, but the formulation is different. And the key point about gray code is that as you move forward by one number, only one bit ever changes. If you look down the gray code as you're going from 0 to 15, you'll see that one bit changes every time. Never any more than one bit, never any less than one bit. And that's really useful for a genetic algorithm because it means that as you alter one bit, you're moving to a neighbor in the search space. You're not jumping all over the place as you would with a conventional binary number. So putting my example chromosome 2,6 into gray code format, you'll see it here. Now, looking at the algorithm itself, the way it works is you start with a randomly generated initial population. Can be whatever size you want. Size of the population is one of very many variables at your control, but let's say typically about 50. You evaluate the fitness of each individual in the population. And then there may be a termination condition, whether you've got close to the targets figure that you're looking for, maybe a certain amount of time has passed, maybe a certain number of iterations, but there's usually a termination condition, and assuming you haven't reached that position, you select your best individuals from the population to reproduce or mate, and they reproduce through a process called crossover. You can also introduce mutation, and then you get a new population that replaces the old one, and you repeat until you reach your termination condition. And then through the principles of evolution, you'll have reached a better solution. So I mentioned crossover is the principal way of reproducing from candidate solutions in the population. And the way crossover works, this is single point crossover, where you take two chromosomes, which I've arbitrarily labeled M and F for male and female. Obviously, there's no such concept really in genetic algorithms. And they swap genetic material to create these children here, where each child looks a bit like its parents. It's got the many of the characteristics of its parents, but the children are not the same. And because you've chosen the best parents, you will generate children which are different from the parents, and the best children will be selected for the next generation. The children that are worse than their parents will die out. We have other forms of crossover. You can divide the chromosome in more than one place so that your swapping of genetic material gets a little bit more complicated between the parents. And indeed, multi-point crossover, where there's several crossover points. And uniform crossover means that you can swap the genetic material at any gene. But the point is that you're basically, the whole point of crossover, though, is that you're generating from two parents, two children, each of which has a mix of the genes from the parent, whichever technique you're using. And it's applied with a probability, a crossover probability. And this is one of many variables that are adjustable. I'll keep coming back to this point during my presentation today, that there are many variables that you can adjust in genetic algorithms. And that makes them both powerful and complicated. And there are many techniques which I'll come on to for trying to set good values for these variables. Mutation is another technique to try and introduce variety into the population. It's to help you in that exploration stage where you're trying to make sure that you're exploring the whole search space. So mutation is a way of introducing diversity by flipping one or more bits. So we started with this individual here, which had a value 1 at this point in the chromosome, and it's got switched to 0. So it's been mutated. So that's basically the idea of how chromosomes represent points in the search space and how they reproduce. And I said you choose the best candidate solutions, the best chromosomes for reproduction. But I now want to talk about how you select. And I'm going to start by talking about fitness proportional selection. What that means is that an individual, a chromosome's probability of selection is proportional to its fitness. So its expected number of offspring is also proportional to its fitness. And there are two common variants. I'm going to start with roulette wheel selection with replacement, and then I'll move on to stochastic universal selection, SUS. Roulette wheel selection, or roulette wheel selection with replacement, is based on the idea of a conceptual roulette wheel where you distribute space around the wheel in proportion to the fitness of the candidates. And then you spin the wheel n times for a population of n. So all individuals have a chance of being selected, but the highest fitness individuals are most likely to be selected. So to illustrate that, if you just imagine a population of just 3, that's a bit unrealistic. As I said earlier, a population of 50 might be more normal. But let's say you have a population of just 3 individuals. X has a fitness of 1, Y has a fitness of 4, and Z has a fitness of 3. You distribute the space around the roulette wheel in proportion to those fitnesses. So Y, as the fittest individual, has the largest share, then Z, then X. And then you spin this pointer, randomly spin it, so a random number between 0 and 1, and see where it lands. And Y is going to be selected most often, X least often, because it's got the smallest share of the roulette wheel. So that's how roulette wheel selection works. But it has some problems. First of all, there's a statistical chance that the distribution might not reflect the fitnesses. Even though X was the least fit, you might just by chance pick it more times. You also have these two problems that are common in genetic algorithms of premature convergence and stalled evolution. Premature convergence is when the selection is too strong and your algorithm homes in on a local optimum. It has not explored the whole landscape before it exploits a local optimum. Conversely, stalled evolution is where selection is too weak. So although the algorithm may have found the general area for the global optimum, it does not exploit it sufficiently. It does not get to the top peak fitness. So to overcome the first of those limitations, selection variance, we have an alternative, which is called stochastic universal selection. And it's a variation on the roulette wheel principle. You divide up this space on the roulette wheel exactly the same way as before, but now there are multiple pointers that you spin only once. So in this example, we now have a population size of n, where E and C have the largest fitnesses, and A and H have the smallest fitnesses. And we start with 8 pointers. All you can imagine them all on a ring, which you spin just once. And where the pointers now land, those are the selected individuals. And this guarantees that the selection is proportional to the fitnesses. So that was a stochastic universal selection. And as I say, that overcomes the selection variance issue. But it still leaves the problem of premature convergence and stalled evolution. So one technique to tackle that problem is so-called fitness scaling, where you adjust the fitness to provide a sort of scaled version of the fitness, sometimes called the selective value. So to illustrate what I mean, during the earliest stages of evolution, what you want the algorithm to do is to make sure it explores the whole fitness landscape, to not be too drawn in to a possible local optimum. So what you can do with scaling the fitness is to squash the fitnesses so that it's less likely to be drawn to a local peak. It's more likely to explore the whole landscape. And then later on, where you think you have found the peak, you really want to make sure it gets to the top of that peak. You want to stretch the landscape so that that's more prominent. So that's what fitness scaling does. An alternative is tournament selection, where you have no roulette wheel at all, and you select pairs at random for a population n. There'll be n pairs, and for each pair, the fittest individual is selected. It's like a tournament between 2 chromosomes, and the least fit individual can never be selected on that basis. Finally, in terms of these variations, elitism is a technique where the fittest individuals are cloned. So if you have your fittest individual in a generation, it will always be cloned into the next generation, which is a useful technique for making sure you never go backwards in terms of the fitness of the population. So I showed you earlier this 2D landscape, but real fitness functions are more complicated than that. Even in 2 dimensions, they can be quite complicated, and it can be quite hard to find the global optimum. And these are 2 test functions called the Schwefel function and the Greinwank functions that we used for testing out different forms of fitness scaling. So this is some work that I did with a student a little while ago, where we evaluated some of the standard fitness scaling techniques using both the Schwefel function and the Greinwank function. And we tested them for the effectiveness in terms of finding the fittest individuals. Here it's represented as a cost. That's kind of like a negative fitness. So basically a small bar is good here. It means you've got the lowest cost, highest fitness value. So you're looking for the small bar here, but equally we're looking for low cost in terms of computational cost, as compared with unscaled stochastic universal selection. So you see tournament selection is very cheap. So it's actually got a negative cost compared with the unscaled standard SUS. And what we devised was actually a system called transform ranking, which was able to transform between different scaling mechanisms as the algorithm evolved. And it performed reasonably well. We've got a pretty small bar here, not as good as this one, but pretty good in terms of the finding a low cost, high fitness individual, and a moderately good computational cost for the Schwefel function. But if you look at a different function, you see some of the other some of the techniques which were good with one are bad with the other. So looking at tournament selection, for instance, really poor at finding fit candidates with the Schweffel function, although it's computationally cheap. But moving to the Greinwag, tournament selection is really pretty good, as well as being computationally cheap. Whereas our technique is actually pretty consistent. Again, we've got a low cost, a high fitness found, and again, a moderate computational cost. So we think we devised an all-round performer, as it were, in terms of fitness scaling when we devised the transform ranking. Right, what I want to move on to now is some of the sort of tweaks and refinements to the standard genetic algorithms. So one of the things you can do to improve a genetic algorithm is to add a local search stage just here. So I've already explained that a genetic algorithm starts with a population, you evaluate the fitness, you select the fittest individuals, you reproduce from them through crossover, introduce diversity through mutation, and then you have a new replacement population. Well, what you can do at this stage, before you evaluate the fitness, is to carry out a local search around each candidate solution to see if it has a neighbor that's actually fitter. And there's two things you can do if you do find a fitter neighbor. So it's local search gradient descent before each fitness evaluation, and it's the Hamming neighborhood. That's just a posh way of saying the nearby candidates. So then you can either, if you find a fitter solution through that local search, you can either replace the candidate solution with its fitter neighbor. That's so-called Lamarckian inheritance, which in the biological sense is considered implausible, but it doesn't matter for a genetic algorithm. You can replace it with the candidate solution, or you can keep the candidate solution, but increase its fitness, substituting the neighbor's fitness, and that's so-called Baldwinian evolution. So that's something you can do to improve the performance of a genetic algorithm. And what we've done is evaluate the effectiveness of that approach by using a mixture of both Baldwinian and Lamarckian, and applying a probability as to how often you use it. So in the case of the Schweffel function, we found that basically it's worth doing it all the time. So if you look at the x-axis, we used 100%, probability of local search is 1, i.e. we used it 100% of the time. And if you look at the mix, the best mix is the square box, which is 100% Lamarckian. So our best solution for the Schweffel function was to use the local search 100% of the time and to use the Lamarckian version 100% of the time. But it's not always like that. If you try a different fitness function, this is a so-called F1 fitness function, we got a different result altogether. We got the best results if you only applied local search 10% of the time, probability 0.1, and you had a mix which was only 20% Lamarckian and 80% Baldwinian. So what we find is that actually the best mix of how you introduce local search is dependent on the fitness landscape. So what we then devised was an algorithm that automatically adjusts the search strategy while the algorithm is evolving. And this is an approach which I'm going to talk about with another example now. But my key message, I think, throughout this talk is there are very many parameters with a genetic algorithm that you can adjust. And the most sophisticated genetic algorithms monitor their own performance and adjust their parameters accordingly. And I want to give you just such an example now, coming back to practical real-world examples. So this is an example of a system that we've called SEXI, which stands for System for Evolutionary Crew Scheduling with Intelligence. And it's about scheduling the train drivers for freight trains. The way the freight industry works, and certainly our industrial collaborator in the UK works, is they work on a weekly time horizon. They take orders from clients they assemble virtual trains, they assign the real fleet, the real trains to those virtual trains. Then they schedule the crew, which is the real bottleneck, the real efficiency challenge, and then they roster, which is allocating actual identified people. So let me just explain now why crew scheduling is such a key issue and something that needs optimization with a genetic algorithm. First of all, there's the issue of contract utilization. In this industry, drivers are contracted to work a certain number of hours per year, and they will be paid those contracted hours, even if they are used for fewer hours. So even if they are employed for fewer hours than their contracted hours, they will still be paid their full contract. On the other hand, if the driver is required to drive for more than their contracted hours, they will be paid overtime hours, which are expensive. So there's an inefficiency there. The unused hours are where you're paying a driver for hours that are contracted and not used. That's a waste of money. And excess hours are where you're paying additional fees to go beyond contract. And in our industry, with this industry partner we're working with, the unused hours are costing them £3 million per year, and the excess hours are costing them £500,000 per year. So £3.5 million per year wasted just through inefficient use of the contract. But that's just one part of the problem. Let's look in a bit more detail about how a driver's shift might work. In this example, in the United Kingdom, every driver has a home depot, and our driver is based at Oxford. So they arrive at work in Oxford, and the first thing they do is to drive their first train. Well, their first train doesn't leave from Oxford, their first train leaves from Bristol. So they have to catch a passenger train from Oxford to Bristol, which then connects with the freight train that they drive. So they can then drive 3 freight trains quite nicely, Bristol to Reading, and that connects with another freight train from Reading to Stevenage, and then another freight train from Stevenage to Cambridge. When they reach Cambridge at 8:30 in the evening, they have another job over at Milton Keynes for later that evening. But if they tried to get a passenger train, there is no direct passenger train link. They would have to go through London, and it would take too long. They would miss their allocated freight train. So what they'd actually do is take a taxi from Cambridge to Milton Keynes, drive their freight train, and then finally at the end of the day, because it's rather late in the evening, they'd have to catch a taxi home again. So that's the driver's plan for their shift for the day. This is what it looks like. It's referred to as a diagram in the industry. And you'll see that they have a shift of 8 hours, but they're actually driving a train for less than 1/2 of that time, 46% of that time. This is a so-called throttle time, this proportion. And they've also incurred additional costs of taxis of £70. And this is quite typical. And there are other constraints. There's a maximum duration of this diagram, this plan of their day. There's a maximum total driving time. There's a maximum driving time without a break, and there's a minimum length of the break. So all these health and safety regulations represent constraints that have to be respected. At the same time, you're trying to maximize the throttle time, the proportion of time the driver's driving the train, minimize their taxi and train passenger trips, and minimize unproductive time. But the overall aim is to minimize the overall cost of the schedule that takes all of this into account. And it's a complex network. The United Kingdom is not a very large country, but it does have quite a complex rail infrastructure with 550 freight trains per day, 3,000 trip legs, and 1,240 drivers in 49 depots. So we applied a genetic algorithm to this task. But just as you saw earlier with the local search, what we did here was apply a different sort of modification. We looked at adjusting the parameters for the genetic algorithm, and specifically the parameters over the selection and reproduction. In fact, we used a fuzzy logic module. I won't go into the details, but a fuzzy logic module is inserted here to adjust the relevant metrics and in response to the statistics. Specifically, what our fuzzy logic system did was to monitor the convergence measure. So that's how well the algorithm is doing towards finding an optimum. The UN is the number of cycles since the last improvement. And finally, the fitness variance. So that's the variance in fitness between the fittest and the least fit members of the population. And according to those variables, it's adjusting the mutation probability, the crossover probability, those two variables to control how aggressive, if you like, the genetic algorithm is in terms of trying to explore the search space. And these are the results. If we start with the blue line, which is our standard genetic algorithm, what we'll see here is that the cost of the schedule, so that's the inverse of fitness. Fitness is something you want to maximize. Cost is something you want to minimize. Conceptually the same, just one's the negation of the other. As you would expect, as we iterate, as we run the genetic algorithm for the blue line, the genetic algorithm finds a lower and lower cost schedule settling around here. But with our fuzzy logic controller, which is optimizing the parameters of the genetic algorithm, so that's fuzzy controlled genetic algorithm, the red line, you can see that we get a better schedule, a fitter, lower cost schedule, faster. So it's a real, really emphasizes the importance of getting the right variables in a genetic algorithm and the power of being able to adjust those variables automatically. This is a screenshot of our system for finding those driver schedules. What you can choose to minimize specific variables such as taxi cost or the number of diagrams, that's the number of those kind of work plans for each driver, or the idle time, but we've actually gone for minimizing the total cost of the schedule. I'll actually show you that live now. Running the actual software. And what you'll see is that the graphs constantly redrawing themselves, recalibrating themselves as they adjust to fit the scale. But you see the cost function is going down and down and down every time, and it's readjusting as we work through. And that's the total cost of the schedule. And this task, as you can see, it's sort of coming to the end now. Yeah, that's done now. Just you have the option to save the parameters. So it only takes about half a minute for what is actually quite a complex allocation task. And if you compare our results with this sexy system to the manual experts, now the people doing it manually are pretty good, but nonetheless, we managed to find improvements, saving a cost of about £5,000 a day on the cost of the schedule, reducing the actual number of drivers required and their payments and the taxi costs. So that's a significant efficiency. And that's before you take into account the efficiency saved by not using human labor to generate the schedule in the first place. Just want to finish off with one final example, which is plasma deposition. And the reason I'm throwing this one example in is to show you that the point I made right at the start is that genetic algorithms are part of an artificial intelligence toolkit. So in this example, plasma deposition is a complex manufacturing process where low pressure ionized gas deposits atoms on the surface of a component here for high value manufacture. It's a difficult process to control, but we built an artificial intelligence controller for this process. This thing called a Langmuir probe measures the electron energy, and it needs to be tuned. So that's where the genetic algorithm comes in, tuning that. But it's part of a broader picture, because you've got lots of things to measure that are highlighted in blue, things to control, which are highlighted in red. And we built an AI system, multi-agent AI system, to do this task. This is what the kit looks like. That's what the plasma looks like through the window. And this is a short video just showing the kit. There's some, you may be able to pick up some sound of some whirring, which is the sound of the pumps clicking in. That's the pump control algorithm. So there's a module specifically controlling pumps. And that's the sound of the plasma fired up, and that's being controlled using fuzzy logic. So fuzzy logic controller for the plasma. And that last screenshot was shown here, which is tuning the Langmuir probe. So this device needs to be tuned. So you've got rule-based agents, which are controlling the pumps. You've got a fuzzy logic agent, which is managing the electrical conditions. You've got a neural network, which is interpreting the optical spectra. And you've got a genetic algorithm, which is also doing its part. You've got all these agents doing their specialist job in a broad artificial intelligence system. Regarding the genetic algorithm, the Langmuir probe is this device that measures electron energy. It has 7 harmonics, which means 7 amplitudes, 7 phases, which needs to be adjusted. So finding the best combination of those 14 variables, so that's a kind of 14-dimensional parameter space, is really hard for a human, but really easy for a genetic algorithm. So to summarize, genetic algorithms, a very practical technique. They use population-based optimization, where each individual is a point in the search space, and it's based on the principle of survival of the fittest. An individual's chance of reproduction depends on its fitness. The use of crossover and mutation give you diversity, and diversity is a chance to explore the search space. So you want to explore the wide search space before you exploit it. That's to say, exploit the global optimum. If your selection is too strong, you get premature convergence and you zoom in on a local optimum. If your selection is too weak, you get stalled evolution and you may get near the optimum, but not actually get very close to it. And there are very many practical applications, as I hope I've shown you today. I wish to acknowledge various people who've worked with me through the fitness scaling, the local search, which is the Lamarckian and Baldwinian inheritance, the rail freight scheduling, and the plasma control example. I need to plug my book, which Professor Lee mentioned kindly at the start. It's just been issued now in its 4th edition, just published within the last couple of months. And if you go to my website, actually, adrianhopgood.com, you will find there at my website, there is a discount code you can use should you wish to buy the 4th edition. I also maintain some resources for artificial intelligence at adrianhopgood.com/AI toolkit. You'll find lots of practical examples there. And I will put the slides from my talk on genetic algorithms on my website. I will do that this weekend. Thank you very much. It's been a pleasure to present to you. I'm happy to take any questions.
Thank you, Adrian. Professor Hopgood's speech, keynote, is a very stimulating, exciting, and also practical, suggests both significant scientific value, research value, and practical implications. I have a quick question. Some noise with a big screen, because the technician is connected a big screen in the room in Cambridge. So I have a quick question. Your algorithm and the combination with fuzzy logic, linking genetic algorithm with fuzzy logic, sounds very interesting. I'll have a quick question, Adrian. can you deal with multiple objectives? For example, regarding freight, trains, and crew scheduling, can you deal with conflicting? Yeah. Can you deal with conflicting objectives? For example, you want reduce the number and the cost for the members, for the number of members, crew members. At the same time, you want to keep customer satisfaction and service quality, and also regarding your helicopter or drone, how can you deal with when you're optimizing the objectives like efficiency, speed, and destination, while reducing the fuel costing, the battery costing, or efficiency and effectiveness things? Are you with me?
Yes, indeed. Yes, thank you. It's an important
very difficult
point.
because according to my narrow knowledge, because I learned intelligent systems from your book, Intelligent Systems for Engineers and Scientists, 20 years ago, 25 years ago. I read your book, but I know it would be difficult for genetic algorithms to deal with conflicting objectives at the same time.
Yeah. Okay. Well, I would like to outline two approaches.
Yeah.
So you saw right at the end, I advocated the use of multiple techniques working together. So one approach would be that you have your two separate genetic algorithms, which will maybe give you two conflicting views on which is the sort of optimal approach. And you can then use another technique, maybe a fuzzy logic technique, to come up with some sort of combination, some compromise between the solutions that are being proposed. That's one approach. But what I've tended to do within the domains of genetic algorithms is design a fitness function that reflects those multiple objectives. I think that's possibly the most straightforward solution. So if you've got something, let's say you quoted sort of customer satisfaction, which might possibly be in conflict with sort of driver efficiency.
Yes. What
you could do is put those together in some sort of combined fitness function where they are perhaps given slightly unequal weightings depending on which is more important to you, or that weighting could be adjustable anyway. There could be a combined measure, and then all you have to do, I say all you have to do, is design your genetic algorithm so that its fitness function is actually that combined measure. So that's probably the easiest way of doing it. I would say that that if the two fitness functions, if you normalize them so they're both in the range, say, I don't know, let's say 1 to 10, you normalize them so they're in that range, and your combined fitness is the average of the two fitnesses, or it could be a weighted average if one aspect is more important than the other. That would be a way of achieving it.
Yeah, this is a good idea and brilliant advice. According to my knowledge, maybe wrong and limited, because genetic algorithms seeks to search optimal solution, the best solution in a limited local area, in the local scope, and if I have conflicting objectives, so your other idea here, so we do it separately, but we need to think about how to link them together, and yes, as you said, make a compromise, and may do ranking or rating for the alternatives regarding efficiency, effectiveness, regarding satisfaction, cost, and or something. Maybe do some ranking, or with a human judgment combined with a managerial judgment, and along with your optimization algorithms and physiologic things.
Yeah, indeed.
Okay, thank you.
As I said in my first bit of the response, absolutely, you can take that sort of approach. You can use literally human judgment, or you can try and capture that human judgment in a knowledge-based agent, which is
Yes.
Which acts as an advisor. The other thing I should just mention in this context is that normally we're focused on finding the best solution, but that's not always the case. In some applications, you're actually quite interested in the suboptimal conclusions. So as a completely different application area, I did have a PhD student who was working on designing games, and specifically a football video game, and used a genetic algorithm for generating free kick scenarios, so that it was not, so from the player's point of view, it was not predictable, and the genetic algorithm, you could produce the optimum free kick, a David Beckham free kick, but sometimes for the game you don't want the best free kick. You could also use some of these suboptimal scenarios from the genetic algorithm.
Okay, thank you very much, Adrian.